Welcome to this special colloquium talk today. It's unusual time, unusual day. So everything is unconventional in our condensed matter physics world, okay? It's my great pleasure to have Dr. Jiarui Li here today, and who is one of our condensed matter physics faculty candidate. This is why we have this special colloquium talk this morning. He has impressed our search committee very much. And so Dr. Li received his bachelor degree from Peking University in China, and then moved to MIT for PhD. And received his PhD degree by 2022, and then moved to SLAC National Accelerator Laboratory for postdoc as it's named fellow. So he has been extremely productive, and he has authored and co-authored so far 24 publications, mostly in Nature series, either Nature or Nature sub-journal. In particular, he has 6 first authored papers, again, mostly in Nature or Nature series. And so it's a great pleasure to have him to give us a talk about his research, and also in particular about his perspective about his science vision. Without further ado, so it's your time.
Thank you, Ronin, for the very nice introduction. And hi, thank you for coming. And I'm Jiarui Li. Today I'm very happy to be here to talk about my research recently on by using these resonant photons to understanding the correlated quantum materials. So before I start, I would like to acknowledge all of my colleagues, including my advisors in PhD and in my PhD and postdoc period. And without the critical contributions of all of my colleagues, the results that I present today would not be possible. So this is the content. I will briefly introduce the background a little bit, and then using 2 examples, hopefully I can convince you that using this resonant photon techniques or in the X-ray energy range, it is a very powerful tool to uncover the microscopic physics in the quantum materials. Okay. So I'm interested in the physics that I'm interested in. It's a common characteristics behind a huge class of emergent quantum phenomena, so such as magnetisms, superconductivities, or ferroelectricities. And the common characteristics behind these emergent quantum phenomena are collective electron organizations, and they are normally typically very long-ranged and well-organized electrons on top of the atomic lattices. And these collective electronic organizations are usually formed under the influence of these many-body electron-electron interactions. And these interactions can often span across multiple degrees of freedoms, charge, spin, orbital, and lattice degrees of freedoms. And the collective interaction between these multiple degrees of freedoms determines the very complex electronic ground state in the quantum material, leads to a very interesting macroscopic electronic functional properties. And when people are trying to study this highly correlated electron-electron interactions, 3D electrons are normally having the highest electron-electron correlations. That's why a lot of studies are performed in this prototypical 3D transition metal compound, where they have 3D electrons. They are highly confined spatially near a nucleus core, as well as these atomic orbitals are highly directional and anisotropy in the space. Therefore, the electron-electron interactions are mostly strong in there. And a lot of as a very good example, a lot of this 3D transition metal oxides are in this perovskite structure with this chemical formula AbO3, where the major player in this structure is the atom in blue, like B atoms, where it sits at the center of this B oxygen 6 octahedra. And this perovskite structure, the reason that this is most of the material, a lot of materials are in these structures, is because that the structure of this kind of structure have a lot of flexibility in hosting a large classes of elements in the A and B sides.
So Jiarui, how are you defining a perovskite structure here? That's an FCC with an addition in the middle?
Yes, but the red atoms are oxygen, so they are the basic structure is still cubic. And then you can see that the most structural framework are the corner sharing this oxygen octahedra network connecting to the up, down, front, back, and left, right. Yeah, but it's normally cubic, but the flexibility of this structure helps. The flexibility in this structure can host a lot of elements with different sizes, and therefore the perovskite structure can have a slightly distortion away from the cubic symmetry, and to accommodate these imperfections in this atomic size.
And the variant is the thing in the middle. The thing that does change that you're changing.
Yes, the blue atoms can have this many choices, and the green atoms can have this many choices. Yeah. And so there are a lot of combinations of elements that can put into this structure, and therefore this compound can have a lot of choices. However, but not every combination of the elements here are actually thermodynamically stable in the atmosphere, in the ambient condition. So in order to stabilize this metastable structure, we use a epitaxial synthesis technique to help stabilize this unstable new phases in the ambient structure, ambient condition. And this is a photo of such a synthesis technique called pulse laser depositions, where a very high power laser coming in and hits a raw material target, and it excites a lot of active atoms, and they got deposited on a pre-selected substrate. So this is a perovskite lattice substrate, and we deposit a lot of atoms on top of them, and this epitaxial relations requires that the atoms to form with the same lattice symmetry as well as lattice constant as the substrate. And there are a lot of choices of a commercially available substrates that we can use, and this helps us to stabilize a lot of 3D transition metal, maybe more than 3D transition metal compounds that are not so available in the ambient conditions. Yeah. So by doing so, people can synthesize a large class of quantum materials. For example, in this lanthanum calcium manganite, that this lanthanum and calcium concentrations can be continuous varies from 0 to 1, and that gives us this freedom to control the electron-electron interactions in the charge, spin, orbital, lattice degrees of freedom in this in this compound, and which leads to a lot of very interesting electronic ground states in the material. And by doing this, people have realized a lot of macroscopic functional phases, such as superconductivities, ferromagnetism, or ferroelectricities. So my goal here is trying to understand this microscopic electronic structures, and how can they corresponding to the macroscopic property of the quantum material. So how do we gain this microscopic understanding of the electronic structure? So let's look at here. If we have a microscopic electronic structure like this, and they are periodically arranged, and one of the natural thoughts to measure them is the diffraction. It's the diffraction, and it is indeed that we do a diffraction, but so all of these electrons are sitting on top of the atoms, and if you do diffractions, the first thing you see is the lattice Bragg peak, as you see that in these black dots. But this extra electronic modulations breaks the translation symmetry of the lattice. For example, in lattice, the translation symmetry is they are translationally invariant after each one translation, but these charge modulations are repeating every 4th unit cell. Therefore, you would expect an additional charge superlattice Bragg peak at a quarter away from the of this reciprocal space. And if you do the similar considerations in the magnetic degrees of freedoms or orbital degrees of freedoms, you will see additional orbital or spin and Bragg peaks. And this is theoretically working, but actually you wouldn't see that in a lab environment. The reason is that the interesting electrons that participated in these complex electronic structures only exist in this valence band. And in the diffraction process, most of the electrons are concentrated in the core electrons, which is here. So the signals coming from this charge, orbital, and spin degrees of freedoms are very weak from the compared to this lattice. And the technique that we use to enhance this sensitivity towards the valence electrons is called resonant X-ray techniques. So it is a technique that we can tune the X-ray photon energy to match the energy level difference between the core electrons and the valence electrons. And one example is shown on the right, that we can first look at the black curve here. This is the absorption, where we can control the X-ray photon energy that's gained across one of these atomic transition edges called nickel L3 edge, which is the transition from nickel 2p level to 3d level. And as you look at this black gray line, that this records how much the X-ray is getting absorbed by the material. And you do see an enhancement of this X-ray photon and the electron interactions when the energy is sitting at this resonant edge. This corresponds to the photons getting absorbed by the electrons and transition the electrons from the core level, 2p level, into the valence band. And we can also look at the other channel in the resonance scattering channel. This measures how much the photon is getting scattered by the electrons. And you also see an even sharper enhancement here. And this measurement is taken at a magnetic Bragg peak. So at resonance, you see a clear magnetic Bragg peak, that you see a very clear diffraction Bragg peak. But when you tune like few electron volts away in photon energy, but while keeping the same Bragg condition matched, such a signal just go away. So this shows that with this resonance effect, you do get a very strong enhancement in the signal or the sensitivity that you can have for the valence electrons in order to probing them. And the theory calculations shows that this enhancement can be more than 1,000, a factor of 1,000. So it is pretty. It is a huge enhancement. So beyond the simply the enhancement effect, the ability to control the X-ray photons also provide another probe to probe this anisotropy of these 3D electron orbitals. And for example, in the absorption regime, like by selecting this X-ray polarizations with respect to the orbitals, you can control the atomic transitions, which control or forbidden a certain atomic transitions. And in the scattering channel as well, by selecting the incident and outgoing X-ray polarizations, you can selectively probing the charge, magnetic, or orbital degrees of freedoms. And having shown you that this technique, but it is unfortunate this technique is not available in the university lab because it costs too much. And where the place that generate these X-rays, they call it synchrotron light source, and this is one of the places that in the US near Chicago. And they orbit these electrons in this storage ring with a relativistic energy scale, like giga electron volts. And then when they want to generate X-rays, they pass these electrons, like relativistic energies, across this alternated magnetic field, and therefore the electron will oscillate in this magnetic field, therefore generates this very highly intense and energy tunable X-rays. So having said that, I'm going to show you two examples of how I use the X-rays to probe the microscopic electronic structures in quantum materials. And the first one is the neodymium nickelates. So neodymium nickelates also has a perovskite structure as shown on the right, and the major player here is the nickel, sitting in the center of 6 oxygens. There are 2 major phase transitions here. This is a phase diagram where you see that we can stuff different rare earth elements on the A side. There are 2 major phase transitions. One is the metal to insulator transition, where the resistance jump for orders of magnitude. And the second one is a phase boundary here that separates the paramagnetic phase to antiferromagnetic phase.
What is this tolerance factor again?
Tolerance factor is how well this structure is approximating to the cubic. If it's closer to 1, it's more and more cubic. But if we are going to the left, it means that these atoms are too small to support a cubic structure.
It's like a distortion.
Yeah. So the lattice will distort and fit the okay, so let's go. So it also has very interesting electronic structure. If you calculate the valence of the nickel, so you have 3 oxygens and a rare earth elements, the nickel should be in their 3+ state nominally. But actually, nickel ions doesn't like to be in 3+ states. And how does it going to resolve it? It will try to grab 1 electron from the oxygen. So therefore, you have a oxygen empty orbitals and with a nickel 2+ state with 3d8 fittings. So in the metallic state. So therefore, we call this covalent ground state. It's 3d8_L. So this L means that there is a hole appeared in the oxygen orbitals.
Is that the equivalent to the oxygen deficiency?
Not really. The oxygen is stoichiometrically 3, but it's just the grabbing the electrons going from the oxygen band to the so it's a negative charge transfer system, or put it in this way. Yeah. So and the mechanism that for it to go through this metal to insulator phase transition is that at high temperature, these 2 nickel sites are equivalent, but in the low temperature side phase, the oxygen will break this symmetry between these two nickel, and it will move towards one nickel, more or less, than the other, forming this expanded nickel oxygen octahedra and compressed nickel oxygen octahedra. And you will also grab one electron from this nickel and put it on the other nickel, forming this 3d8, L0, and L2. So this is called bond disproportionation. And this is equivalent to forming a three-dimensional checkerboard lattice of this, say, charge density wave that opens up a energy gap at the Fermi energy that make it into a insulator. Last is that when you further cool down, there's an antiferromagnetic order that orders along one direction with a ordering wave vector quarter. And the magnetic structure is believed that they are ordered ferromagnetically in the plane that perpendicular to this ordering wave vectors, but repeats every 4 plane. And since I mentioned that there are 2 equivalent nickel sites, so we can label them nickel 1 and nickel 2. So every other plane, say nickel 1 plane, they are having the anti-parallel nickel spins, and so does the nickel, and so does the second plane and the fourth plane. So the black spins are anti-parallel, but ferromagnetic aligned in plane, and all of the blue spins are also anti-parallel across 2 adjacent planes. And the magnetic structure, so the whole magnetic structure can be modeled by this only 2 spin motif. And the magnetic structure of this compound has been studied since 1990s by neutron diffractions, and they pointed out that it should be a collinear magnetic structure where it should be up, down, or left, right. That nickel 1 and nickel 2 are all parallel, in line with each other. But later on, more and more study has discovered that it could be a non-collinear, that where these 2 spins can have can add an angle. So why do people are so interested in this magnetic structure? Because there are theories that predicts that this material can be a possible type 2 multifluoric material that couples with the magnetic phase transition. And this becomes really interesting that in this material there's a metal to insulator phase transitions and also a coupled magnetic phase transitions. And right now they are trying to put this ferroelectricities in these materials as well. So this indeed include add some additional functionalities to the material. So the determination of the magnetic structure can tell us what could be this multiferrotic coupling between the magnetic structure and the ferroelectric polarizations.
So what are these letters for? S, T, N?
Oh, they're standing for 3 different magnetic phases. So N is non-collinear magnetic structures, and T is they have ferromagnetic magnetic planes running in these diagonal directions, and S is they have this magnetic structure that in this squared building blocks and repeats in the checkerboard side. So they name it S and T. Yeah. So why is this magnetic structure so hard to determine? And the reason is that in order to determine this vectorial magnetic structure, because it's a vectorial field, and all of the measurements that we made are actually projecting this vectorial field along some directions or into some plane. And after these projections, any of these non-collinear or collinear magnetic structure are being equivalent after this projection. Therefore, a lot of measurements cannot distinguish between these 2. And what we're thinking in our perspective is that these non-collinear magnetic structures can actually be probed by the circular polarized X-rays, because when you have a non-collinear magnetic structures, there exists a chirality in this magnetic structure. Say, for example, we can have this right-handed circular, spiral magnetic structures, and we expect it to interact differently with a circular polarized photons when they're in the diffraction process. So with this idea, we just bring the materials, we grow the materials and bring them to take these measurements. And here is the magnetic Bragg peak. And you can view this as a line cut on this across this magnetic Bragg peak. And this measurement is taken with different X-ray polarizations. But what I want you to focus on this circular polarizations, green and red. So there are indeed a differences in this scattering strength of when we measure it with this circular polarized X-rays. And from this single measurement, we can prove that this is a chiral magnetic structures sitting on this nickel sublattices. So to have further information on these magnetic structures, we do additional technique called azimuthal rotation. So this way, we have during the diffraction, we have the K in and K out, and this satisfies the Bragg condition, and this azimuthal rotation is the rotate of the material along this momentum transfer, so that the Bragg condition is always satisfied. And here is the photo that during the experiments to show you how this is performed. So since the Bragg condition is always satisfied, but we are actually modulating the relative orientation of the magnetic spins, or it could be orbitals as well, at relative to this photon polarizations. And we took the measurements, shown on here with different X-ray polarizations. We see that the magnetic Bragg peak intensity modulates as we rotate the sample systematically. And there are twofold rotations, there are maximums, minimums. And by some models, like fitting this, by fitting this azimuthal modulations of the magnetic Bragg peak intensities, we can actually obtain the magnetic structure. And it's shown here that it is indeed a right-handed magnetic spirals. And with nickel 1 and nickel 2 are at a, if we're looking at from the top, the nickel 1 spins and nickel 2 spins are at a 90 degree apart, with a factor of 3 differences in the magnetic moments. And there are further information that we can extract from this kind of measurements, as we see that there exists two high symmetry position. For example, azimuthal angle at 0 and at plus minus 90, like 0 and 180 or minus 90, where the magnetic Bragg peak intensity is maximized or minimized in the two different channels. And this corresponds to that the magnetic moments are in and outside of the scattering plane. And this is very interesting, that by selecting the polarizations at these two spatial angles, we can selectively enhance or reduce the photon and spin interactions on half of the spin sites. So for example, in this site, this position with a pi polarizations, we can enhance the spin photon interactions in this orange clusters. But if we switch the polarizations, we're suppressing those half of the spin sites, but enhancing the other spin sites. And as we scan the energy across these nickel resonances, the spectral shape tells us what is the magnetic scattering form factor, or you can relate it to what is the electronic structure of the spins. And since we have this enhancement or suppression, we can measure this spin spectra for two different spin clusters. And by some mathematics, that treatment from these two measurements, we can obtain this nickel magnetic form factors as here. And this is corresponding to their electronic structures as well as the magnetic moment sizes. So the magnitude or the height of this signal is proportional to the magnetic spin moment. And this is roughly 3 times larger in the F1 in nickel 1 rather than compared to nickel 2. So there's a factor of 3 consistent to what we have for the magnetic crystallographic measurement. And then they show a very highly similar spectral shape despite this common factor. And this is really puzzling to us that if we assume that spin nickel 1 has the magnetic moment of 1, so it is a spin 1 system, then the spin nickel 2 should be the spin of the nickel 2 should be a 1/3, which is close to spin 1/2 system. And we know that in these atomic configurations, spin 1 system and spin 1/2 system should behave very differently in the electronic configurations, but then it's very unlikely for them to have a very highly similar electronic spectrum. So how do we resolve it? So we try to recall that in a very old concept in cuprates called Jiarui singlets. This is when you dope a cuprate. When you dope a cuprate, the doped electrons exist in the hull of the oxygen orbitals, but they surround it around one copper site. So the copper site has a spin 1/2, and this doped oxygen holes also have spin 1/2, and they form a singlet to cancel out the spins on a single site. So we're thinking here, like in our pictures, we have a 3D8 in clusters in one side and 3D8 with 2 ligand holes on the other side. And what we believe is that we have nickel spins that are having the same spins on each side, but then the oxygen ligand holes are having forming this Jiarui singlet-like structure that to reduce the spin size on the compressive nickel oxygen clusters. So in the end, we ended up with this period of 4 magnetic structures with a large spin, small spin. So we call it this spin disproportionation phase. So I still have some time. So having finished this part, I want to switch the gear into a second topic where, in addition to this, to using this resonant photons to probe the electronic ground state, very complex electronic ground state in this transition metal oxides, I want to show you how we can use additional sample control method to manipulate the microscopic electronic structures in a ferroelectric material, strontium titanate. So strontium titanate here also has a perovskite structure, where the titanium right now is the major player, sitting at the center of the titanium-oxygen octahedra. And it has the tendency to develop a ferroelectricity, where these titanium atoms tend to move away from this high symmetry point to seek for a energy minimum in this potential well, double potential well. However, this motion never happens, even at 0 temperature, even down to 0 temperature, because that the quantum fluctuation of this in the position of these titanium atoms are strong enough to overcome this potential barrier to delocalize these titanium atoms to at the one side, either side of the of the barrier. So there is a competition between these quantum fluctuations and these energy minimization actions. And since this phase involves a displacement of the atoms, strain is a very effective tuning knob in controlling this ferroelectricity in the material. So a lot of people and theorists as well propose that there is a quantum critical point sitting in between this ferroelectric and paraelectric phase boundary at the t equals to 0 termination. And also there are people trying to use epitaxial thin film synthesis to realize this as TL in different strain states that realize this ferroelectric order in the thin film. However, in order to study this quantum critical physics at temperature 0, you would like to sit at the temperature 0, but have some tuning capability going along the horizontal direction of this phase diagram that crosses this quantum critical point. But right now, most of the people only have the capability of changing the temperature in the system. And so we want to attack this problem from another point of view, from the material side. So by using this epitaxial thin film synthesis, we use a so-called freestanding oxide membrane technique. So we synthesize a stack of oxides materials with a intermediate water-soluble layer, strontium aluminate. So we have a substrate. We epitaxially grow another layer of strontium titanate, and we grow our strontium titanate film on top. And when we dissolve this intermediate layer, we can release the top layer that what we want into the water, and they are 20 nanometer thin, like few nanometer thin, and millimeter sizes, so that we can manipulate them as what we do in 2D materials. Like we can transfer them, stack them in different geometries. But in this study, we try to laminate this strontium titanate on a polyimide thin film. You can think of it as a plastic, and it's soft and it's stretchable, so that we can apply strain very easily. So this is our methodology. When we try to apply strain, we characterize their lattice constant through diffraction. So we measure multiple Bragg peaks, and through refinement. So when you look at this, the Bragg peak moves back and forth as we apply and release the strain, as we stretch the material and we release it. So you see that the Bragg peak position moves back and forth. Correspondingly, the lattice constant getting stretched up and released back. So through refinement, we know that the A lattice constant getting stretched by more than 1%, and it is reversible. This is very interesting because normally in this kind of materials, it is ceramic and they're brittle. So like your dish plates, and when you drop it on the floor, they tend to just shatter. And so does this material. So when we synthesize them in a bulk form, they are very brittle and they tend to break with about 0.1% of strain. But when we get them down to this thin, we are able to stretch them super elastically beyond 1%. We can even go further. There are publications suggesting that it can go up to 5 to 8%, but they're not reversible at that point.
So what's causing this reversibility? Why is it so resilient?
So we believe that it's the reduction of the one dimension. So since we reduce the thickness dimension down to a nanometer, and so we get more flexibility to release the strain through the interface with the vacuum. Yeah, and I can show you later. I don't put it in my slides. We have a thickness dependent of this, how much it can go. Like when above 50 nanometer or 100 nanometer, it behaves as the same as the bulk. But then if you go down to 10, 20 nanometer, it's enhanced. Yeah. Okay. So this is the basic characterizations of the lattice mechanical property of these nanomaterials. And in order to going into the physics, so we measure the ferroelectric order by this titanium K edge absorption, which is around, the photon energy is around the 5 keV, 4.97-ish. And this is the photon energy, and this is the absorption of the X-ray from the by the titanium electrons. And we observe that when we increase the strain, there's a systematic change in this absorption X-ray absorption spectra, that this peak is getting enhanced. How do we understand it? This feature. So so this feature is actually corresponds to the 1s transition to 3D transitions of the in the titanium electron levels, core levels. So in the paraelectric phases, the system is centrosymmetric, and from 1s transition to 3D transitions, this angular momentum changes is 2, which is not possible. It's dipole forbidden by a single photon excitations. Therefore, there is no such a peak and only a weak bump, and that is a higher order thing. Like you need a quadruple transition is allowed, but that's a details. So basically, in the centrosymmetric structure, this dipole transition is not allowed, so you don't see a strong peak. And when we stretch it, it breaks the inversion symmetry, and such a transition becomes allowed. Therefore, you see an enhancement of the peak, and the peak height is this transition probability is proportional to this p square. It's proportional to this ferroelectric order parameter square. Okay. It's proportional to this order parameter square. And also, like, it's also directional. If we change the X-ray polarizations not along the where the ferroelectric order it's pointing, we don't see this peak as well, as you can see from this here. And we take these differences is corresponding to this ferroelectric order parameter squared. We can track this signal as function of strain at different temperatures, and we see a very highly temperature dependent evolution of this strain and ferroelectric order parameter. So we can reconstruct a phase diagram. First, we can identify a phase boundary between paraelectric phase and the ferroelectric phase, and this is the phase boundary, which is very similar to what people already know in the literature. And then when we look at this, ferroelectric order parameter as function of strain, we find that it is a second order phase transition without a very sharp jump. And we can perform this, and also they have very highly temperature dependent critical behavior. Like you see that they have a very large curvature at 20 and 40 Kelvin, but they straighten out at higher temperature around 100 Kelvin. So we perform a power law analysis to fit this critical exponents of this ferroelectric order parameters as function of this strain. And what we find is that the critical exponent beta is temperature dependent. At higher temperature, 100 Kelvin, it is around 0.5, and when we cool it down to 20 Kelvin, it starts to increase towards 0.7, 0.8-ish. And from the mean field theory, if you do a Landau theory calculations to calculate to see how it does the ferroelectric autoparameter should behave as function of strain, you would get a 0.5. So what we believe is that it goes from this classical phase transition at high temperature, where this ferroelectric, where this autoparameter strain critical exponents is it's around 0.5, and when we cool down, it deviates from a classical phase transition regime. Since the quantum fluctuation gets stronger and stronger as we cool down, and therefore this system is deviating from a classical model and entering a quantum phase transition regime. Therefore, you see an enhancement of the critical exponents. And this is also consistent with this measurement taken like decades ago in a single crystal strontium titanate, where at high temperatures, when you measure this dielectric constant, the inverse of the dielectric constant follows this Curie-Weiss law very nicely until it goes below like around 100 Kelvin, and it deviates, suggesting that when you suppress the thermal fluctuations, the quantum thermal fluctuations, the quantum fluctuations gets prominent, and the system entering a quantum regime rather than a classical regime. So we believe that we're demonstrating a crossover from a classical phase transitions to a quantum phase transition regime in this strain phase diagram, strain temperature phase diagram.
I'm curious, why did it not go down to lower than 20 Kelvin?
Yeah, because this is a diffraction experiment, and this is the base temperature that we can have in short.
Really?
Yeah, so we need to have an open space and cannot have a shield to do better radiation shielding. Okay. Yeah. So yeah, so hopefully through these two examples, I already show you the power of these resonant photon techniques in unveiling the microscopic electronic, magnetic, and magnetic structures of these quantum materials. And I also show you this how can we use this synthesis, novel synthesis techniques that to control the quantum material properties using a new methods. So in the future, I plan to combine this simple synthesis technique either from heterostructures, thin films, or membranes, and combine it with the synchrotron resonant photon scattering techniques, including spectroscopies and imaging as well, and plus the controllability capability of in these quantum materials to explore the new organizing principles in the microscopic point of view in the quantum materials. So I would like to carry out research in three categories. In the first one is that I want to use these techniques to gain insights into the microscopic electronic structures. For example, we can understand the microscopic electronic arrangement in a quantum materials, and this includes the electronic crystals and also the complex mechanisms that have a lot of spintronics applications, and also we can try to visualize the different electronic domain structures, because they sometimes can have forms different kind of domains due to these phase competitions. And second, I would like to explore this collective electron dynamics, because this offers insights into how is the low energy Hamiltonian of a system, or what is the leading interactions in the materials. and this includes like static spectroscopies of measuring the EK dispersions of the elementary excitations in the materials, or we can have some excitations and then measure the ultra-fast relaxations or dynamics of the systems. And in the third part, I would like to use a novel techniques of controlling these quantum functionalities that can be potential technologically useful for the future. So for example, I can use strain. I already demonstrated the strain inducing ferroelectricities, and strain can also be used to strain magnetism in the quantum materials, as well as the ferroelectricities and resistive switching as well. And current pulses is also widely used in the in switching of this quantum materials, and yeah. So with that, I will put up my acknowledge slides, and thank you for attention.
Thank you very much. Oh, sorry. So we're on. Question, comments?
I have maybe a silly question. So one of your slides, you show the resonant X-ray scattering, and also there's like a X-ray absorption side.
Yes.
And there's two different spectra, but both of them you're scanning the X-ray in energy, right?
Right.
So why would it have different behavior? Is one that are you detecting specifically along a certain direction?
Okay. So there are two reasons. The first one is that the X-ray absorptions only is a photon in measurement, and it only measures the attenuation of the X-ray. So it's it doesn't have a momentum resolution. So it's everything averaged out, like everything added up. But in the resonance scattering, you are measuring the scattering of the lights of the X-rays, and therefore it's a Q not equals to 0 measurement.
Okay.
So they could have a different response.
Okay, so it's a direction specific.
Right.
Okay.
Right. And also, from the absorption point of view, it measures the imaginary part of the response function. But in resonance scattering, it both measures the real part and the imaginary part, but squared.
Right.
So you see two different spectra, yeah, depending on this, because there are two different microscopic process.
And another one is for the spin disproportional, like the explanation that you have,
Yeah.
like where you have one spin and then there's another spin that's orbiting it. So that would be a kind of like a structure as well due to the electron. So can you pick that up as a pattern or no, in a diffraction? Just curious.
In principle, yes, but currently the limitation is that since this structural distortion is happening on the oxygen atoms only right now, and in the normal, like regular X-ray diffraction, oxygen doesn't contribute too much because it only has 8 electrons, and so the oxygen intensity is very low, but either in neutron or X-ray electron diffraction. People don't pick this up that much. And one idea is that you can use resonate with oxygens, but the oxygen edge is at 520 electron volts, and the range in the momentum space is not long enough for us to reach that Bragg peak.
Okay.
Yeah.
Thanks.
So the magnetic moments for both nickel 1 and nickel 2 were determined directly from your X-ray
Yes.
absorption measurement, right?
Yes.
So with this, yes, this Zenrise singlets, by the way, they are still both alive, so it's not that old, okay?
Okay.
So just to give you a perspective, they both are my, Rise was my thesis committee. So anyway, my point here is, is that the kind of quantum effect from your point of view? And why this effective spin is somewhere about 1/3?
Yeah, it's okay. So yes, it is. It's a multiplicative effect because since this is a many electron ground state, and this is not a pure state, so it is if say, let me go back to that slide. So it is not a pure state. So it's not a, you cannot say that it is a singly spin 1 or 1/2. Like what I say here is 3D-A with a ligand hole L, but actually it's not, because this is a very covalent bonding between the nickel and oxygen. So this will be a mixture of 3D8, L, and 3D7 and 3D9. So there's a coefficients in the front. So there are just a macroscopic amount of these configurations in these subspaces.
Well, in this case, again, we also had another study in another oxide. Actually, oxygen side has lots of polarization.
Oh,
So
yeah.
that would be in combination contributed to the net spin
right.
or movement.
Mm-hmm.
Right? Questions, Mas?
If you go to the slide where you're inducing the non-centrosymmetric phase in strontium titanate.
Sure. Like this one?
The one, I guess the one where it's a couple later, I think.
Okay.
Yeah, okay, no, that's fine. Go back to the, yeah, right. Is this a general property of ferroelectrics that if you had a non-centrosymmetric ferroelectric, which already exists, and you strain those, do you change the degree of non-centroism of that material? In other words, do you make it more non-centrosymmetric? Is that a general property? Or is it unique to this material, to a material going through this phase transition?
It should be generally get larger because it's determined by the atomic potential. So, like if you already have a double well potential and you are stretching them apart, you are basically stretching away these two bottom away from each other. So you expect a increase, but I cannot say it for all of it. I think that's a general trend.
So you basically dislocate the central atom more.
Right.
This is basically what the net effect would be.
Yeah, but whether that affects the electron it
does.
affects the core electrons, but the way it affects the valent, the ones that are polarizable, I don't know. That's more.
Well, basically the dipole movement would be in proportion to that distance, generally. Really?
On the left, the structure there is centrosymmetric and also kind of rotationally symmetric. So is this a uniaxial ferroelectric, or is it kind of more, you could stretch it along any direction and see the same thing?
We could, in this experiment, we're stretching it uniaxially. So, yes, it is. But we also try to stretch it. There's no predetermined direction, but as long as we can stretch it along one direction, it is like, it will happen, go
so
along.
The potential is actually much more interesting looking without stretching, because it's got
there's slightly
several equilibrium positions.
Yeah, there's slightly some anisotropy along this high symmetry directions, like 1-1 or 1-1-1 directions, but most of them can be realized. Like in barium titanate, it has a very interesting phenomenon that as you cool down, they will first develop these directions, and then it rotates to 1-1-1, and then rotates to 1-1-0 as function of temperature. So Yeah, so it's possible. They're very close to each other in the minimum energy minimum. Yeah.
So my understanding is that basically the strain stabilized the metastable state, basically. Does this make sense to you?
Kind of. Yeah, it's.
All right. So side.
So when you apply strain, the double wire potential can be strongly affected by this strain. But can you
Right.
comment on the effectiveness of the strain on the quantum fluctuation?
Okay. So the effects on the, I think they are the same thing, because the quantum fluctuations is determined by the curvature at the bottom, right? Or and also you have this, it's okay, the photon frequency is determined by the titanium and oxygen mass mostly, as well as the interaction. Interaction is interaction is determined by this curvature of the potential. So they should be roughly comparable, like the same thing. If you are stretching away, then instead of changing the mass, then you should be able, then the quantum fluctuation or the 0 point energy should be roughly the same, or changing as the curvature changes.
I'm just guessing maybe the
Yeah.
strain doesn't make strong contributions to this quantum fluctuation, and since it's mainly governed by the mass, atomic mass.
That is, yeah, and right, and because there are people trying to use isotope replacing the titanium atoms, and they do see it does changes the suppressing the quantum fluctuations. Yeah.
So it is related to the mass of the atom.
Yeah.
Right. Okay.
So you just increase the trapping potential? Or so the fluctuation cannot drive in between the two sites?
Yes. So you imagine this is a summation of two parabolic potential, and then
So it's just a little deeper.
right.
But can it still tunnel across? It's still a little barrier that.
Yes, you can check this paper. They have possibilities, but depending on this the barrier height, that the frequency can go from terahertz to very slow. So in that slow time scale, we typically consider it static.
Okay.
Yeah.
I forgot.
It's lunchtime. Yeah, that's right. Everybody's
Okay.
schedule is pretty tight. Let's
Okay.
thank our speaker one more time.